happy today to talk about some of the landscape of high-performance computing, and I call it the Comedy Club. Hopefully you will understand why. And looking at how low-rank matrix approximation can actually play a big role here in bringing some coherency across all those various architecture. Before that, I'd like to give some acknowledgement of my team members and collaborators from KAUST, as well as our astronomers from Parvis Observatory and Australian National University, our computational scientists from the KAUST Supercomputing Lab, and the list of our vendors with whom we have been collaborating for years now, from NVIDIA, AMD, and recently from GraphCore and Cerebras. All right, this is the system on which we have been running, for the last few years. If you look at it, so I'm listing the main vendor behind, the architecture solution that consists on those supercomputers, and I'm also putting the ranks in as listed from the list of 500. If you look at those systems that we've been playing with so far ourselves from our center, we can see Intel, AMD, IBM, NVIDIA, Fujitsu, ARM, and all their programming environment, their architecture, their own proprietary networking, many ingredients that constitute those systems are clearly important for us to understand how they work at the node level, at the system level, from various perspectives, to get the performance out of it. And those are the main vendors that I have been listed. Adding here to this list, NEC, NEC. We had access to a large cluster from NEC in Japan, where we explored opportunities for one of our applications that I will be discussing today. And if you take this one step even further, there are also AI customized or specific hardware that gives deep learning type of workload a tremendous performance improvement. So that's the sort of HPC/AI Comedy Club, with all their challenges and opportunities that comes with those. Shaheen 3, this is our own supercomputer that have been announced last year. The system should be deployed in production by the end of this year, early next year. It's a Shaheen 3 supercomputer, 25 HP Cray supercomputer cabinets, delivering over 100 petaflops per second. Just to give a perspective from Shaheen compared to Shaheen 2, it's 20x time faster than our current deployed system. It will have two partitions, one CPU partition based on EPYC Genoa, around 4,600 compute nodes, and another partition which will have mostly GPUs composed of 2,800 NVIDIA Grace Hopper super chips. This is the NVIDIA CPU GPU packaging that provide memory coherency between the host and the device. All those are connected via Craig Slingshot interconnect, delivering high throughput. The interesting thing that we have here at KAUST, and that helps a lot in really some of the challenges we are tackling in our own center, is 2/3 of KAUST faculty use Shaheen for computational modeling and simulation. That helps a lot when it comes to having multidisciplinary research projects across campus. And then the four main topics that Shaheen 3 is supposed to tackle and embrace all the challenges related to energy, renewable, environment, food, water, and healthcare. So this is our own hardware landscape that we'll have to deal with in Shaheen 3. Two partition, one CPU partition based on this EPYC Genoa. It's a typo, it's not Milanix, and NVIDIA Grace Hopper. So we're having those two architecture very different, right, in terms of programming environment, architecture. So one application may or may not be able to run on each of those partitions, except if some level of abstraction are provided within the application, to be able to have a single source code that will operate, separately on those two partitions. And because it's not enough, as I mentioned before, there is also all those new AI customized chips that are mushrooming out there that are really developed for deep learning workload and have also their own hardware characteristics. Some of those hardware characteristics I am highlighting those in red. We are dealing with high cache capacity, for instance, for Genoa or Milan X. We are also dealing with support for mixed precision for Grace Hopper, chips that do extremely well for deep learning workload. How we as domain scientists reconcile? How do we reconcile this hostile environment as you look at it with our HPC scientific applications, right? So it's really a daunting challenges, but it comes with many opportunities as long as we are ready to embrace them, right? And the way we want to tackle those various systems, one approach that we're trying to promote is we like to look at our activities in our center as an hourglass, where we have the many applications we have to support and many architecture we have to deploy on. And we like to see ourselves located at the waist of that hourglass, trying to identify common infrastructure among those various applications, so that we can put ourselves in a situation where we have one stone, multiple birds, if you will. And for that, we try to matricize as much as possible our application. And I'll explain why, I believe, in the next slide. By matricizing, I mean, we try to solve linear, equation, system equation. And what we are calling for here is, the idea of reshaping, linear algebra for massively parallel architecture. And the way we want to do this is by, enhancing user productivity by using layers of abstractions, exposing parallelism, using fine-grained computation, achieving scalability with asynchronous execution, and whenever possible, exploit data sparsity using low-rank approximation. What I mean here by data sparsity is not about the structure of the matrix where you have zeros and non-zeros element of your matrix. What I really mean is what we've seen in many matrix operator from natural problem that we try to simulate out there. There is sparsity in the data. So the data looks like it has information, but it turns out that only minor information may be conveyed by specific blocks in my matrix that characterize the problem. And the whole idea is that how can we, only operate on the most significant information carried on by this matrix operator. And here comes low-rank approximation that would not only reduce the memory footprint, but also decrease the arithmetic complexity of your problem, allowing you to solve much larger problems and allowing you to scale up further. And even as I would demonstrate in my later slides, it actually also turns out to be an extremely good method to exploit or to extract bandwidth from caches on various architecture. And one of the other challenges is how we maintain code portability, right? And by using matricization, you formulate your problem in terms of matrix operation for which we know that hardware vendors will provide cool hardware feature that could accelerate and provide mixed precision, for instance, optimization on those operations that are well supported by those vendors, right? So that's yet another aspect that I'd like to highlight here. So those are the applications we've been mostly working on in our center. I mean, in our group, part of our center, 3D geospatial statistics for climate weather prediction, mesh deformation for CFD application, seismic imaging for oil and gas and renewable energy, 3D computational electromagnetics for radar application, for instance, wireless communication for supporting 5G networks, and computational astronomy for ground-based telescopes. So among those 6 applications, we had several collaboration and nice outcome coming from those collaboration with vendors, with industry, some award from the research community, and cool application we've been working on. We got a few publication out of those work, and we are extremely happy about those. Here are the two applications that I'd like to focus my talk today: seismic imaging and computational astronomy. And I decided to pick those two because they have this common infrastructure that we identified. And with that, we are really able to cater, the challenges encountered by domain scientists in those two fields. And I'll start with, computational astronomy. That's probably my oldest project I've been working on since I joined KAUST. And this started back at 2012 when I met out of pure coincidence my collaborator that I've been working with for now almost 12 years at this NVIDIA GTC conference. And what we've been working, or what we've been supporting with our kernel here, several major ground-based telescopes, including the Very Large Telescope. This is a European consortium. The Subaru telescope, this is the main flagship telescope by Japan, and the future European Extremely Large Telescope that has not been built yet. It's still under design, and just to give you the size of this huge telescope that will be deployed in Chile, you can see some of the small tracks, on the picture that gives you a relative size, which has, I think the dome has a height of 100 meters, and this is a massive, device for astronomers. And each of those telescopes have their own instrument, right? They have their own instrument that basically in real time are in charge of, collecting the data, collecting the information coming from, remote stars via lights. And those instruments are trying to basically do an X-ray, if you will, of that light, looking at the various wavelengths and deciding or understanding, what may constitute the atmosphere of those remote stars via the light that they propagate, until it reaches our atmosphere, and eventually those mirror on our telescope. So there is the MAVIS. This is for a very large telescope. XEXAO, this is the name of the Subaru telescope, the name of the instrument deployed on the Subaru telescope. And you have also other three instruments that are currently designed for the European Extremely Large Telescope. And I'll be focusing mostly on the MAVIS here, MAVIS instrument, and this is mostly led by Australian national universities and their astronomy department. This is the main issue for astronomers. For all ground-based telescopes, the main challenge is how to outsmart the atmospheric turbulence. So the atmosphere is great for human. It's a great protection, as everyone knows, but it's a nightmare for astronomers because it distorts the trajectory of light rays. And this is well seen here or captured with this, compact camera. When you observe the sun, for instance, you can see that there are, some shading around the sun and image is blurred, and that's clearly an element that is problematic for studying the light of those remote stars. So the way of fixing this is to use adaptive optics. It's a technique well known in the astronomy community, and it is used for giant telescopes. And the idea is that you want to control in real time, right, the shape of the incoming wavefront, and basically tell how those tiny mirror that compose the big diameter or the big mirror of the telescope, how they should tilt in real time to compensate for the atmospheric turbulence. So, the main keyword here is real time. You have to compensate for what you see, not for what you have saw, 10 minutes ago. And this has to happen, at a high frequency, so that you are able to, get the proper understanding of that remote stars, and then, decide what you want to do afterwards with this. So it's a complex, mechanism behind the big eye of the telescope, and the main keyword here is this real-time processing, and the operation that turns out to really drive, the complexity of the system is this matrix vector multiplication. Yes, a level 2 blast operation. That is the main kernel across all ground-based telescopes. And that was sort of, shocking for me when I got to know this a few years ago, of course. And then, while I initially thought, well, I mean, it's just a MADVEC, right? It's a memory bound kernel. Not much can be done out there, on this basic level 2 BLAS operation. Well, it turns out that there are really cool stuff that can be done. And this is what I'm going to show, I believe, in my next slide also. So this is just a cartoon showing these deformable mirrors and how they have to tilt in real time by those actuators that push and pull each of those tiny mirrors independently to compensate in real time for the atmospheric turbulence. The outcome of those MADVEC that we do, the vector solution we have, is the magnitude at which we should pull or push each of those actuators, right? And this has to happen really in real time. So this is the instrument. Again, the name of the instrument is called MAVIS. And in terms of improvement in terms of science from an astronomy point of view, it's a really leading edge instrument. It's able to scale up the whole AO concept to even more number of actuators, provide faster control system, and it's a fast track project with the first slide by 2026. And what the astronomer claimed that it is even deeper and sharper than any space-based instrument that do not have to deal with the atmospheric turbulence. They are located in space. So that's very interesting, actually, as a claim. And this is what astronomers working in MAVIS are saying. So what we did here when we looked at this MADVEC, matrix vector multiplication, we looked at the, trying to understand this matrix, not only its structure, although we know it's a dense matrix, but looking at, the information it conveys, trying to identify any opportunity for approximation in terms of low rank, in terms of low rank approximation. And the idea is quite simple here. You look at the matrix, which is typically short and wide. Well, short, I mean it has few number of rows than column. And the matrix sizes come from the measurement of the various, sensors, whether they are wavefront or, laser guide stars, for instance. And this is how you get to know them, and the number of actuators as well. And this is how you calibrate your matrix. Typically, this is the shape. It's a rectangular shape. What we did is we take that matrix and we split it into blocks. And each of those blocks, we try to, run a compression algorithm, which is, the SVD, singular value decomposition, which is the, the workhorse of linear algebra. This is how we call such, this algorithm. And we try to capture the most significant information on each of those blocks, right? And on the top left here figure, I'm showing a heat map where I represent the ranks with the color here. So basically, black and reddish colors indicate, opportunities for compression. For compression, because the ranks that we get at the end is much smaller than, the size of the time. Okay, so that's because it's much smaller. Then you could actually compress each of those individual blocks. And then once you've done that, see if not only you're able to go faster, obviously, but ultimately you want to make sure you also have the proper accuracy at the end. You have not altered the science output. This is yet another way of looking at this heat map. It's a rank histogram. And anything that is below 150, which is half of the tile size, roughly, anything that is on this side here indicate that it's such matrix is a great candidate for doing low rank approximation. And this is how it turns out that the MAVIS MAVIS data set is resilient to low rank approximation. So when we had that findings, well, I mean, we had to work closely with our domain scientists to make sure that we are able to reproduce, or not reproduce, but get the expected accuracy that does not alter the science output. All right, so this is our MADVEC. I'm just gonna quickly show how we do this, right, from an implementation point of view, and how we do this operation. So that's my dense matrix, which is rectangular. I just take it 4x6 style for the purpose of the example, and I split it into blocks that are also dense. And what I do first thing is I compress. Okay, I take each of those style and I run SVD-like algorithm, and I represent now my initial dense style into two small matrices that are short and wide and tall and skinny, those U bases in blue and V bases in green. And those two bases, if I were to calculate the outer product, I'll be able to reconstruct my dense type, okay? But what I want to do is I want to compress, save in memory footprint, but also in arithmetic in complexity. I want to compute now all my operation in real time, but now using those two guys, those two tiny matrices that represent the most significant information on each of those types. So the way we do this, there are three phases, okay? So there are three phases to do that. But before this, for memory, accesses and optimizing of memory accesses, we stack those bases. We take all the V bases and we stack them up. We take all the U bases and we also stack them so that we have a contiguous memory access. Once we've done this, we enter the three phases that characterize now my matrix vector multiplication. It used to be one call to level 2 plus, right? When the matrix was dense. Now, because I compress, I change my data layout, and I have to operate differently. And I have to express now the original operation into three phases. The first one is taking the V bases and multiplying by those vectors using a batch matrix vector multiplication kernel. Okay, it's a batch because I have to simultaneously run the matrix vector multiplication operating on those bench of V bases and multiplying by the corresponding X vector. And I do that for each of those group of bases within my structure that represent all the V bases. And I have to do this simultaneously, right? Because they are embarrassingly parallel. And I won't be able to have high hardware occupancy if I were to run them one after the other one. So I need to ideally design a kernel that do this matrix vector multiplication in a batch way with the strong assumption that the size of those matrices could be of different sizes. Here, for the example, I'm showing constant sizes everywhere. But obviously, that's not the case because some tile may contain more information than others, and that translates into higher ranks than others. And therefore, my matrix vector operation, involve various matrix sizes, and that's a problem too. I mean, it's a kernel that is not actually well optimized on vendor numerical library. That's when it is implemented. But most of the case, unfortunately, it's not even supported. So we find ourselves alone, if you will. And of course, it's an opportunity for us also to contribute and provide the missing kernel and feature that are needed here for providing high performance. So that's the first stage. We take care of the V bases. We do that first batch MATVEC. All right, and we get that YV structure here. It's a transient structure that we need to project back to the U bases in preparation for the other operation that will involve now the blue guys, from the U bases here. And that third and last phase is also a batch matrix vector multiplication, right? And I'm doing this again by taking a few U bases in a row, approach and splitting them in a row basis like this. And I do a MATVEC with the corresponding, YU data structure, and I get my final Y. Okay, and this is again on, relying all on batch GMV calls with variable sizes. I want to insist on this because we are the edge, if you will, for when it comes to linear algebra and high performance computing. And it turns out that we need those kernels that have not been implemented yet. And some vendors are really working on it and providing those features. It will definitely help if deep learning, for instance, workload would need such a kernel. Then we could just get it as a byproduct for free. But unfortunately, for now, GMV variable sizes, not so many people out there need it, and therefore the priority of those vendors may not be high for providing such feature. But that's okay. We survive with various features and work around, and at the end we still are able to support those applications with high performance. So at the end of this MATVEC, we get this Y vector, right? This is our final output. That's the vector that contains the magnitude at which I should pull, the system, the AO system, adaptive optics system, should push or pull each of those actuators on my telescope. All right, so we talked about low rank approximation. It's an approximation. When you say approximation, it's lossy. Okay, it's not lossless. It's not a compression algorithm, using binary compression, for instance, right? It's really algebraic compression, and therefore you have to lose accuracy. But the catch is, maybe we can lose accuracy in some of those blocks and control properly how much we can afford to lose, so that when we get the science, outcome, the operator, the astronomers will look at it and say, hey, it's like no compression was happening, right? So I don't even know if we still call this a lossy compression, knowing that, to start with, astronomers have been oversolving, right? Have been really oversolving for decades. And now that you can compress and deliver accuracy as if, nothing happened, I'm not sure if we should call still this lossy, compression when you know about the outcome of the science. So, it's something that we may want to discuss it afterwards. But, I really found it cool that, we could provide such, linear algebra operation with many knobs to give the proper accuracy for the astronomers. So that's here a heat map. We're looking at the accuracy threshold. So that's the accuracy threshold used to trim, the additional singular values that are not counting toward, the main significant information of the tile, right? So we can afford to remove them and therefore obtain those compressed or two short and wide Orlensky matrices that we play with. So that's the accuracy threshold here. And we look at tile size, right? I said the matrix, we tile it into small blocks. And this tile size is a tuning parameters, right? And this is what I'm showing here. What I'm showing here for the heat map, when it's green, it means it looks good. That's the stray ratio. That's the metric typically used for astronomers to determine whether we are good or bad, if you will, from the science output. The number that you see on the on the matrix here is the theoretical speed up, right? So of course you reduce memory footprint, but you go much faster because you do less operation in this matrix vector multiplication. And what we identify here as the proper tile size for some of the systems we've been running on and the data set that we've been playing with is typically a tile size of 128 and an accuracy threshold of 10 to the power minus 4. That will give us roughly a speed of 3.6 and give a satisfactory stray ratio in green. So that's typically the guy here that we tune for. So we're happy. We identified scenarios for which we are, from an accuracy point of view, we are covered. Now we can move to performance, right? So we check the, I would say most important condition, to get the right accuracy, and then we can carry on now with performance. This is the list of hardware we've been running on: Intel, AMD, Fujitsu, NVIDIA, and NEC. This is x86, system. So Intel Cascade Lake, AMD EPIC Rome. And we use MPI plus OpenMP here to do the proper affinity on single node, right? This is all single node performance. I mean, the system that needs to do this real-time business on the, on the telescope cannot be a supercomputer, right? They don't have a power plant next to the supercomputer, next to the, telescope site that is really remote, to afford to get high performance. They're really looking at architectural options that are really dense in terms of delivering computational power, right? So this is all single node, performance that I'll be showing. So this is running x86, and I use MPI plus OpenMP for doing affinity. We use Fujitsu ARM MPI plus OpenMP as well, to get the proper, bandwidth from those CMG. We run also on accelerators on AMD and NVIDIA using ROCm and CUDA, respectively. And finally, we use also NEC vector machine, and we use MPI plus OpenMP to run on those fat cores on the vector machine. We can also distinguish all those systems with HBM versus non-HBM, right? And last but not least, I just want to bring your attention to this guy, right? This tiny poor guy, x86 EPIC Rome, that sounds like by itself out there, but actually stand out. stand out from the crowd because of this huge last level cache, 512 megabytes. Okay, and this is huge compared to all the other, all the other system that I'm highlighting here. And what we are trying to do now with this low rank approximation, because we compress, all of a sudden the data set now fit in the last level cache, while before it could not fit there. We were running at the speed of the main memory. Okay, and that's something that I'm going to show here. This is a sustained bandwidth. Okay, so the higher the better on various systems. And comparing, in green the dense. This is dense matrix vector multiplication. No optimization, no compression, no approximation. We just run the level 2 blast operation, memory bound, as opposed to the blue bar, which is the TLR-MVM matrix vector multiplication, where we compress to the proper accuracy, and then we do the operation, on the compressed data set. So the higher, the better. And we used, a batch MV call here with, it's actually variable sizes. It's a typo here. I'll fix this later. And, the bandwidth that we get is just, tremendous here. 1.4, terabyte per second, because we fit in L3 large cache of the EPIC-ROM, right? And we are able, this is a standard x86, right? And those are accelerators, virtual machine, ARM, that, have HBM, have, all sort of cool stuff that, when you fit in cache, you can really fly pretty well. So that's the sustained bandwidth. And this is time to solution. So the lower, the better. And we can see that with EPIC-ROM, we're able to get closer to, 100 microseconds. And this is really very close to, actually, it's actually beyond what the astronomers were expecting. And as you know, with AMDA low, when you optimize the bottleneck, then the bottleneck goes elsewhere. And the whole adaptive optics mechanism they have deployed there, there are other parts now that becomes the bottleneck compared to this MVM that was initially the bottleneck. That's Roofline performance model, and on EPIC-ROM, and as you can see for this kernel, we decouple from main memory. We purely focusing on this L3 bandwidth. We are after this L3 bandwidth, and this is how we can get good performance. Those are latest results that I just with Yushi Hong, my student, run last week on various AMD x86 generation, ROM, Milan, Milan X, and Genoa. And one can see that Milan X, ROM and Milan, the bandwidth is similar from main memory, right? And you can get close to 1 terabyte here for the various Mavis configuration. You get a performance boost when you run with Milan, thanks to the proper cores bandwidth ratio. Milan X give you an additional capacity in your last level cache, and then you get that performance. Genoa basically decrease the gap between bandwidth of cache and main memory, and this is how you're able to get slightly better than Milan X bandwidth. Those are preliminary results, and we're still trying to understand why and how. I have another actually graph, but I'm not showing it here, that demonstrates actually Milan X outperforming Genoa. As soon as Genoa goes to main memory, as soon as our kernel on Genoa goes to main memory too many times, and Milan X then is able to recover and get first place. So there is more to the story, and I won't talk about it, but there is the case of mixed precision also that can be made for this operation. So now we're talking about combining two stuff: low rank matrix approximation, that's purely algebraic compression, and on top of it, also try to save further time to solution, reduce time to solution by using mixed precision. And it's not mixed precision in terms of computation, but it's mostly on storage, on data movement. Okay, we store in lower precision. As soon as the data comes into registers, we do on-the-fly conversion and compute in higher precision. And we can actually combine both, and that's one paper we submitted a few weeks ago that discussed this. And there is actually a very good opportunity here to have a synergies between those two approximation methods and get the best when we combine both of them together. This is the story on MAVIS instrument, and it's supposed to be deployed on the very large telescope. And this is the outcome that you would get with MAVIS, as opposed, so that's your model, okay? That's your ground truth, if you will. That's, Hubble telescope. This is extremely large telescope. This is James Webb telescope, and this is when you do MAVIS on Earth, right? On the ground-based telescope, and you're able to get much better, reconstruction of your signal, of the light that you receive than other approaches. So MAVIS is a critical instrument that is cheap to actually maintain because it's on Earth, is deployed on the telescope, as opposed to instrument that may be deployed in space. All right, so that's the story on astronomy. All right, I'll move to now the second application, seismic. The good news is I'm not having another half an hour to discuss this, because the Taylor-Rank matrix vector multiplication, that's the common denominator to astronomy and seismic imaging. So I don't have to explain again how we compress this this matrix operator, because I already introduced it in astronomy. But that's really the general idea here that we found out works well also for seismic processing. So seismic processing here, the idea is the following. We try to do an X-ray of the subsurface, trying to identify oil, gas, and perhaps also empty layers, layers with air, so that you could take maybe sequestrate, let's say, CO2 from the atmosphere and put it in there. So it has some energy renewable or some carbon reduction in mind as well when we do the seismic processing. And the main operation for this is also matrix vector multiplication. But the problem with this operation in this field, it has not been actually optimized or try to leverage on current architecture, simply because the data is so huge. They have to deal with a large amount of data, and it's not worth it from computational complexity to look at this method, right? Well, when we looked at it, in our case, we proposed this low-rank matrix approximation to leverage this kernel, and then it become an approach that is a good alternative to what has been done out there, while giving a good accuracy. And so 80% roughly of this seismic processing can be spent in doing this matrix vector multiplication, right? And so without having too much detail on the application itself, but I'll be happy to delve into this during the Q&A session if any question were raised. But this is also the same story that I showed there in astronomy, right? So you approximate each of those dense tiles. The matrix is typically, close to a square matrix. It may have some rectangular shape, but still it has M and number of row and column, similar typically. And we compress each of those tiles, and now we do this operation. The catch here compared to astronomy is that here we do complex. Okay, it's complex arithmetic. In astronomy, it was real arithmetic. So there are much more now pressure on the memory footprint, right? So we double because we have to store the real and imaginary part for this application, which was not the case for astronomy. All right, so before we look into this matrix and how we can compress it, there is really cool stuff to apply first. And this is beyond just seismic application. We actually applied it for CFD. We applied it for climate. The idea is we need to reorder the matrix, right? We need to reorder the matrix so that correlation that are expressed in the matrix, we make sure that those correlations are expressed among among two factors that are next to each other. In this particular case, the source and receiver needs to be located next to each other because they will have a stronger correlation. Stronger correlation means higher ranks. And if I were not to do those reordering, then I may not be able to store in memory footprint, save in memory footprint as I wanted, right? So we want to do reordering to really gather most significant information around the diagonal of the matrix that is shown in red, and keep the off-diagonal elements or off-diagonal blocks with lower ranks as much as possible, okay? And that reordering is important again. So we looked at the conventional ordering, we looked at L1 ordering. Those are different ordering we applied on a land or sea survey here done by the ship that you can see there. And we can see the heat map of the matrix change big time. So before the most, the information were sort of, scattered across the matrix. Now it's much more focalized, right? It's much more localized, I mean, around the diagonal. And then, that's important because we know that we can, safely, if you will, decrease, or approximate, the off-diagonal blocks. So we use this Hilbert ordering that comes actually really from the CFD community. We were not really familiar with this, and then we plug it into the seismic application, right? So we are saving big time here in memory footprint, but also in arithmetic complexity thanks to our ordering. All right, so this is a real application. We run on it, and we're showing basically the cost of doing matrix vector multiplication on many frequency matrices. For this particular data set, there are 230 of them of size 26K by 15K. Those are the description of typically of this data set. That is a well-known data set developed by the Society of Exploration Geophysics and European Association for Geoscientists and Engineers. All right, so what we do here, right, we always start when we talk about approximation. We can't move to performance if we are not already having confidence on the accuracy, right? And that's what we do here in the slide. We're checking the traces of 8 receivers and making sure that the accuracy threshold that we use to trim those additional singular values and compress and then do the operation on the compressed data set, we are able to get the traces as if or close to the original implementation, which do not have any approximation. And it turns out that we are able to find this accuracy threshold and the proper block size that would give good performance. This is right now currently typically empirically determined, right? This block size. So it's something that actually performance engineering can help a lot in maybe identifying a proper block size, depending on the architecture where you are running. But the accuracy threshold, this is 10 to the power minus 4, right? So anything that is below that, you can safely trim it and get something very similar to the ground truth. All right, so now we're confident with the accuracy, and there is another actually slide here showing the impact of this matrix vector multiplication when we incorporate it into this post-acquisition processing to remove some of the related noise or effect from the free surface. And that's the velocity model. And every time when we introduce our matrix vector multiplication, we are able to remove those noises and capture the velocity model we had initially. All right, so this is the performance. And here I'm only looking at constant rank. It's a synthetic data set. Okay, so it has nothing to do with the seismic data set that I'm showed before. Here is just to show some performance trend. Okay, so this is running on synthetic data set, and I use constant rank, so there are no issues with load imbalance. I just use constant ranks and show, and those are the ranks here, right? And show the performance I'm getting basically in terms of bandwidth on Genoa, Milan X, Milan Rome. So the interesting thing is there is a crossover here between Milan X and Genoa. And this, this is when basically the main memory bandwidth, which is double of Genoa, which is double of Milan X, is able to kick in, and then you will get Genoa performance in terms of bandwidth much higher. I mean, slightly higher than than Milan X. But for the regime with lower ranks, Milan X is able to get you really high performance. Of course, assuming you are able to fit your data with such small rank that at the end ultimately will give you accuracy. But this is just a synthetic, data set just to give you a flavor of what can be achieved on those various architecture. Okay, so there is a cache bound, if you will, and memory bound. If you were to sort of, create a line that distinguish, the performance between, when you are bound by the cache and the memory bandwidth. This is real data set. Okay, we're taking those 210, I think, or 30. 200, I think 200 or so, matrices, and so I'm showing here for each of those matrices. I'm showing the bandwidth that I'm getting. So those matrices are indexed, in increasing order, and the one with lower index basically are getting lowest bandwidth performance simply because we are able to approximate big time here. Okay, we are able to compress those matrices with lower index much better than others, right? I mean, this means that the information, the critical information, is mostly carried by matrices with higher index. That's what it means, basically, right? But then you can see that when you're going to schedule matrix vector multiplication for each of those matrices in parallel, you will have to come up with some load balancing strategy, to mitigate, the workload that you have when you deal with various matrices. And what you're getting here is low saturation of your bandwidth and high saturation here, simply because of the workload that you're operating on. It's much smaller for smaller indexes than higher indexes. Summary. Algorithm first, right? I hope I made justice to this statement. Everything starts with the algorithm. If you have a nice algorithm, nice way of expressing parallelism and capturing the most significant information to do compression, algebraic compression, and do computation on the compressed data set, you could really do cool stuff. And it's actually what we've seen by being able to enter AI, hardware landscape. We've seen, a gigantic here, interest, at least for those few applications that we mentioned. So we really think low-rank matrix approximation are key for solving, those challenging scientific problem at scale, right? Because it also tackled the memory footprint for large data set. This matrix formulation can actually reconcile, those various workload with the hostile hardware landscape, or comedy club, as I called it in the beginning of my presentation. So we could use GraphCore and Cerebras, hardware, AI-focused hardware for HPC scientific application. Next week, I'll be presenting an IC, paper about how we use GraphCore for delivering performance out of 4 applications. And last but not least, I think we should definitely be after cache size and bandwidth whenever possible. And the trend, as it looks like today, I think vendors are really putting much more capacity in caches, whether GPU or CPU. And I think it's a great opportunity for application and kernel developer, as long as we are able to leverage those. With that, we are recruiting at KAUST, and I'll be happy to talk more about it offline if you guys are interested. And I'd like to thank everyone who attended the talk, and again, Georg, for having me today. Thanks.
Are there any questions or comments?
So in your, for example, this telescope problem, so this matrix, right? So is this matrix created from the light or something that is coming from the telescope, or how is this matrix created? Does it need to be every time computed? That's the question.
That is, yes, absolutely. Very good question. So yes, this matrix has to be, so it's created from wavefront camera. So from measurement coming up from those wavefront camera that are located, next to the telescope, the mirror of the telescope. And, I'm just trying to get this one. And so this matrix basically is generated every, I would say, maybe second or less. And then in between the next generation, you have to use it like 100 or 1,000 times doing your MADVEX. So you basically can compress once and then do your MADVEX as fast as you can before the matrix, another matrix get generated. And again, you compress and then you multiply it 1,000 times, use it 1,000 times.
Okay, so your SVD cost can be negligible in this case.
That is correct. That is correct. Although, I mean, here I showed all my results based on an SVD, the standard singular value decomposition, which is the optimal, if you will, algorithm for doing this operation. But of course, it has high cost. It does not come for free. So there are other, compression algorithm, mostly the randomized SVD. There are also sampling approaches that enable to create the matrix directly in its compressed format. So there are other approaches clearly out there that can further mitigate the cost of the compression phase, which you're right, it does not come for free.
Yeah, thanks a lot. Thanks a lot for the interesting talk.
I have a question connected to that. If the matrix is only recreated every second or so, does that mean that the whole system is only able to adapt to variations in in the reflection of the light through the air in a 1 second frequency, so 1 hertz frequency.
It's actually,
so anything that happens faster is not captured.
Absolutely, but 1 second is actually wrong. Look, I mean, it's written in the slide here as 1 millisecond. So the whole pipeline latency has to be 1 millisecond. So yes, the whole thing has to happen really in real time, or else you would be, you will be basically doing this correction, right, on something that has already passed. So it's crucial to get this real time processing.
You said that, I mean, it says here on the slide, the latency must be below 1 millisecond. And with all the performance data that you gathered using your optimized algorithm, what is the minimum hardware that you need to fulfill this requirement? I mean, obviously, you don't need these 6 CS2 wafers to do the job. Okay, that's just showing off. So how much hardware do you need, actually?
I mean, so today, right? So today, GPUs is the hardware solution on those, on those GPUs and some CPU technology. Mostly, I would say, old Intel, CPUs are mostly today. Those are the technology deployed out there. Okay, so astronomy, community, I would say, like, many domain scientists are really looking at all this hardware innovation from an angle like, is it for me? Maybe it's not for me. And only few will actually adopt GPUs. And I was lucky enough to work with one of them that, is really embracing anything that compute in a fast way. But clearly, today, if they were to propose, a solution that are, I would say the AMD x86, EPIC, processor is one that can answer their challenges, today without too much change into their workflow. Okay, with this high, level cache. But they are constantly looking into, improving the resolution. And improving the resolution means that your adaptive optics, systems become even more complex. So this matrix become even more, larger, right, to deal with. And if they want to further go toward that direction, they clearly will have to consider, either GPUs or some sort of, customized maybe AI hardware, to include in their pipeline. But again, this is really at the edge, and it's a community that is usually conservative because of the amount we're talking about, right? This extremely European, extremely large telescope, the world biggest eye, as they call it. It's a European consortium, and it's over 1 billion euro, right? So it's huge money, and it's a complex system. And one part of it that is critical is this real-time aspect of this matrix vector multiplication. But there are other parts that needs also to be taken into consideration when deciding what you want to do in one segment, of your pipeline.
I have actually one more question. So you told you have multiple vectors, right? Like it can be that you have 1,000 vectors or something, but are they independent? So can you actually perform matrix multiplication? Oh
no, so they are really independent. They come from the measurement, real-time measurement of those sensors. Yeah, I like your spirit. Though, because this is it. We've seen also many situations exactly as you explain here, where you could really cast MATVEC into MAT wireless. For instance, this wireless communication. If you come, we have a paper on exactly this application at ISC this year, which will be presented by Adel Daba, who works now at Jülich Supercomputing Center. He joined, I think, last month, the center in Germany. And he showed for wireless communication, indeed, matricizing, not only in terms of, data structure, but also, doing matrix multiplication for an application that also require real-time, this wireless communication. Not only real-time, but also it has to be energy efficient, because that module needs to be deployed on those base stations that contain those antennas and helps people communicate with each other.
All right, so our time's up. Thanks again, Hatem. Have a nice day. Bye-bye.